Hello everyone, this is part 2 of section 16.2, line integrals. Last time we saw an example where we were given x and y both as parametric equations as functions of t, and we found their differentials, and we substituted pretty much standard procedure, the xy and the differentials, and then evaluated the resulting integrals. This one's a little bit different because y is given as a function of x. And so in order to be able to integrate, we have to have it in terms, each integral in terms of a single variable, okay, either x or y. And if we look at the x dy integral, we can see that based on the fact that y squared is x, if we substituted an x in that integral, then we would be able to integrate that, because then x would be y squared, so we'd have y squared with dy, which is readily integrable. And so then the choice here is to either get this as a function of y, and that's easy again because x is given explicitly in terms of y, but then we had to have to replace the differential dx to be in terms of the differential dy. So here we're going to calculate the differential dx. So the derivative of y, the differential of y squared is 2y dy, and that'll be the differential dx. So now we can make the substitutions, and we'll have the integral from, and also notice that these are given as points. So initially I'm going to say from 4 to lower limit 4, -2 to 4, 2 of, and then I'm going to replace x by y squared, and then we have minus y, and then replace the differential dx by its differential in terms of y, 2y dy. And then we'll have similarly plus the integral, and again I'm going to initially just say the point 4, -2 to the point 4, 2 of, and notice that x is staying constant in terms of the point as well, so that's further motivation to change it in terms of y. But then we have the x, which is y squared, and then times the differential dy. So if you wanted to separate it into two pieces again, I'll just say Roman numeral 1 is going to be the integral. And now I'm going to say from, instead of saying from, well, let me carry along. Yeah, I'll do 4, -2 to 4, -2. But let me, of this, I'll just recopy it for now. Okay, and now I'm going to bring out the 2. Actually, no, I'm not going to bring out the 2. I'm going to rewrite this at the integral from -2 to 2, because now I'm explicitly in terms of y. And here I could just distribute the 2y. Make this 2y cubed minus 2y squared with respect to y. And then that's an easy integral. So we get 2y to the 4th over 2, or 2y to the 4th over 4, so that would be 1/2 y to the 4th, and then minus 2y cubed over 3, so minus 2/3 y cubed, and that would be evaluated from -2 to 2. Okay, so now by the fundamental theorem of calculus, upper limit goes in, so 1/2, 2 to the 4th, minus 2/3, 2 cubed, and then from that subtract the lower limit goes in, so 1/2, -2 to the 4th, minus 2/3 times negative 2 cubed, and that gives us 16 over 2 is 8 minus 8/16, and then minus, this would be 16 over 2 again, 8 minus, and this would be, well, actually it becomes a plus because negative 2 cubed is a negative 8 times negative 2 makes it plus 16/3. And however you do your arithmetic, I don't know, I just see the 8's cancel, and then minus 16/3 minus 16/3 would be minus 32/3. Okay, so that's the first integral that I called number 1, Roman numeral 1, and then the second integral calling Roman numeral 2, and that's just y squared dy with those limits of integration. So this we can integrate, and we'll get 1/3 y cubed. Okay, and then I'm going to say negative 2 to 2, because those are the y values, those y ranges from negative 2 to 2. So then upper limit goes in, 1/3 2 cubed, minus lower limit goes in, 1/3 negative 2 cubed. Okay, so that'd be 8/3 plus 8/3, or 16/3. And so then we get that Roman numeral 1 plus Roman numeral 2 is the negative 32/3 plus the 16/3, or a negative 16/3. Okay, so then one final concept for this section, and it is work as a line integral. So we know that work is equal to force times distance. So we have, in terms of vectors, the work is along the curve is the vector field F times the displacement as a vector, dr. And note that dr is always equal to xi plus yj, and it would follow then that dr would equal the differential dx times I plus the differential dy times j. Now, one thing I'm not sure exactly if I think I said the word times here. This is not times, this is actually the dot product. Okay, so here's an example, and we want to evaluate the work. Here's the function. So the first thing to do is find the function dotted with dr. So the given curve here is, so the displacement function is r of t is a vector is t squared I plus t cubed j. So therefore we know that x, because r of t is equal to xi plus yj, we know then that x of t, or let's just say x, you could say x of t if you like, but let me just say that x is t squared. So from that we get that x is t squared and that y is t cubed. Now the reason why we need that is because we need the differential dx and the differential dy. So that is this x and y here for r in general are these functions of t. So, and you could probably do this without having to peel them off to the side, but I just want to show it explicitly. So dx would be 2t dt, and dy would be 3t squared dt. Okay, so now we have that our the differential of r. So now it follows that the differential of r is the differential dx. Here, I'll write it out using the general formula again. Dxi plus dyj, that this becomes that dr is equal to 2t dt times I, because that's your dx, and then plus 3t squared dt times j, because the 3t squared dt is the dy. So this is the dr that we're going to use in the calculation for f dot dr. So now we'll say that f dot dr is equal to okay, let me do it like this. I'll use brackets here. X cubed minus y cubed I plus xy squared j, that because that's f, dotted with the dr that we just found, the 2t dt I, and then plus 3t squared dt times j. Okay, so recall dot products. I dot I is 1, j dot j is 1, I dot j is 0, j dot I is 0. So you're just multiplying the i's together, basically. So you get x cubed minus y cubed times 2t dt, and then plus the j's multiplied together, xy squared times 3t squared dt. Okay, and then if you wanted to at this point, you can go further, because I mean, you could start the integration right away if you wanted, but ultimately we know that we need this expression in terms of t's, okay? And so therefore, if you want to take care of it now, I think that's what I'm going to do. I made that enough. It's supposed to be an error. Okay, if you want to transform them now to be in terms of t's, okay, x cubed, but what was x? So you have to go back up here to what we originally determined for x and y in terms of t. So that x cubed, x is t squared, so t squared cubed minus y is t cubed, but that has to be cubed, and then times 2t dt, and then plus the x again is t squared, the y is t cubed, but that has to be squared, and then times 3t squared dt. Okay, so now f dot dr is simplifying this. We get, well, let me bring the 2t out in front this gives t to the 6th minus t to the 9th times dt. And then plus, this is just t to the 6th, t to the 8th, t to the 10th. 3t to the 10th times dt. And now let's distribute that 2t. So you can do your algebra any way you want. I guess I'm taking a lot of steps here. But we get 2t to the 7th minus 2t to the 10th times dt, and then plus 3t to the 10th times dt. But then ultimately, because of the fact that these are both differentials of t, we can make it a single integral. And we could say this is 2t to the 7th minus 2t to the 10th plus 3t to the 10th times the differential dt, which then simplifies to be 2t to the 7th plus 1t to the 10th with respect to t. Excuse me, because minus 2t to the 10th plus 3t to the 10th, of course, is just 1t to the 10th. Alright, so now we're ready for the work. So the work is the integral of the curve over the curve f dot dr. So that's going to be the integral. Okay, for the limits of integration, go back up to the given. The curve here was defined, negative t ranges from -1 to 0. So lower limit -1, upper limit 0. And now that's just the 2t to the 7th plus the t to the 10th with respect to t. Alright, so that integrates easily. 2t to the 8th over 8, or 1/4 t to the 8th, plus t to the 11th over 11, or I'll write 1/11th t to the 11th, evaluated from -1 to 0. And then we plug in the upper limit of integration, and we just get a big 0 because t is a factor and t is 0. And then the lower limit of integration is -1. So here we've got 1/4 -1 to the 8th plus 1/11th -1 to the 11th. So I guess that becomes minus positive 1/4, and that makes it a minus 1/11th. And so then find your common denominator, 44. That's 11 minus 4 is 7 over 44, but you got the negative out in front. Okay, so that's our work. Alright, so feel free to do your algebra any way you want in terms of simplifying FDR like I did, and then substituting when I simplified it completely, or you can simplify it within the context of the integral, so it's your choice. Alright, so that's the end of 16.2. We'll see you when you're ready for 16. I believe we're going to point 3.